Hello. So here we have to discuss degenerate energy levels. So till now we already discussed some non-degeneracy cases. So if you look at the previous classes, I mean ground state, helium atom, and these are all non-degeneracy cases. Torque effect of plane rotator, and this one is yeah charged oscillator in an electric field. These are the examples of some non-degeneracy case, enharmonic oscillator. Yeah. So many things we discuss step by step non-degeneracy cases. Okay, these are the energy corrections also. Now it's time to discuss uh, degeneracy cases. Okay, so before uh, explaining this theoretical way, we need to spend a little bit time on this uh, degenerate. What is a degenerate? And we already discussed what is degenerate, not degenerate. So since we are discussing here non-degeneracy case, now we have to spend a little bit time on the degeneracy cases. Okay. Now, now we are going to spend some time on degeneracy energy level. So what is degenerate or degeneracy energy level? So I'm going to be saying this one. We take one example, px, py, pz orbit. If you observe here, the energy level of the system is orbital p. Here, energy is same, but wave function of the system is different. This type of systems are called the degenerative energy. Okay. In the here px, py, pz, same energy level. Okay, I mean same energy state, p orbital, right? But the wave function is different. Corresponding the wave function is different. So this type of cases are called the degenerative or degeneracy energy level. In case there exists one wave function and one eigenvalue, that type of systems we're going to call non-degenerate energy level. So here the wave function is very important. The wave function is very important. The unperturbed wave function wave function. So you need to focus on wave function here complete. Okay. For example, unperturbed wave function is a unique one in the non-degeneracy case. non-degenerate case, when a degeneracy exists. So we need to combine the wave function linear combination. A linear combination of degenerate wave function. For simplicity, consider a case in which e power 0 is, for example, two-fold degenerate. So let us introduce two wave functions. One is psi n power 0, another one is, these are the this en energy level, I mean this eigenfunction is corresponding to the eigen wave functions of the system. Okay, a different function be eigenfunction, and their corresponding eigenvalues we already discussed. One is en power 0. Energy is same. Okay, no need to worry about this energy level. That is a degeneration. And a linear combination of these two be, so suppose I'm going to write like this: wave function pi equal to some constant Cn sin power 0 plus some constant psi l power 0. This linear combination wave function is very, very important. So here onwards, we need to focus more on this type of systems, okay, where the Cn and the Cl are the constants. This is equation number 1. This is the first step. Okay, now we are going to calculate the first order correction energy. Okay, second order correction energy. Not going to here second order correction energy level. That is very, very difficult. Up to I can go this first order correction energy level. Okay. So first order correction to the energy. Okay, that means lambda power 1 order. If you don't know this first order, second order, third order, just go and watch this series. Especially playlists are there. The perturbation theory, the basic derivations, first order and second order correction energy levels. So this is we already know this first order correction energy equation. I mean this equation. Okay. I mean lambda power 1. If you compare the both left and right side of equation, then we can get this equation. Okay. En power 1 sin power 0 plus En power 0 sin power 1. And this, if you consider this one is equation number 2, it may be useful. All these steps are very, very important to understand the degeneracy case systems. So now I'm going to replace psi n power 0, our new linear combination wave function. En psi n power 0, first one, plus Cl psi l power 0. And multiply from left by bra vector. Is bra vector. Okay. So observe carefully. I'm going to use this equation number 2 in place of psi n power 0. Here psi n power 0 is there. Here psi n power 0 is there. I'm going to replace in place of psi n power 0. I'm going to use this one. At the same time, I'm going to multiply from left side of the equation by the bra vector. This bra vector. So if you do this same time, then you can get this equation psi n power 0 h prime in place of this one cn psi n power 0 plus cl psi l power 0 plus psi n power 0 h naught. I mean unperturbed Hamilton, this one. Okay, this is perturbed Hamilton equal to en power 1 psi n power 0 cn psi n power 0 plus cl psi l power 0 plus en power 0 psi n power 0 psi n power 1. Okay, so here I'm going to do one thing. If you apply this unperturbed Hamiltonian or this wave function, then you can get a eigenvalue equation, right? This equation h psi equal to e psi, right? So I'm going to replace this one, the E side. So energy is scalar, right? Then I can write in front of this bracket. Then you can modify like this. Okay, let's do one more step here. So I'm going to split this one also at the same time. Cn psi n power 0 h prime psi n power 0 plus Cl psi n power 0 h prime psi l power 0 plus, so this is eigenvalue equation. I'm going to replace E side, this one. Okay, this is En power 0 psi n power 0 psi n power 0 in ground state wave function. Here also I'm going to write this one like this. Okay, this is Cn En power 1 first thing, then n and n. So this is n, right? This is n. Okay, plus Cl, Cl. Here the En is there, En power 1, and here n, here the L. Okay, then I'm going to write like this. Else you can use same function. Why we are using different notation? Just wait. I'm going to use same notation. Some people may get confusion. Okay, psi n power 0. Right. This one psi l power 0. One more term is there, plus n power 0 psi n power 0 and psi n power 0. So if you observe this equation clearly, these two terms are going to be cancelled. Okay. So here the different state is orthogonal, right? This one is 0. Here because of this is the n state, this is L state, it is going to 0. Then the remaining equation is like this. This notation we can write this notation Cn. This is perturbed Hamiltonian n by n. Okay, this one we can write h n n plus this notation. This is h n. Don't change these places n l. Okay, cl. This is also perturbed term of Hamiltonian n l equal to, here the same states are there. What does this mean? Psi star psi equal to 1, right? Normalization condition. Then we can get here the remaining term Cn E n power 1. So this is equation number 3. Or else you can better to write this one like this. Then we can use equation number 3. Okay, I'm going to write this equation like this for my simplification. Okay, this is Cn. Now it is good. H prime NL to C. This is equation number 3. Equation number 3. Now multiply equation number 2 same thing. Now multiply equation 2 from left side by L power 0 and same time replace n power 0 is our new linear combination of, right? So if you do the same calculation what we done above, okay, then you can get this type of equation. You can multiply the same term by using these words, okay, then you can get this type of equation. That is, I'm going to directly write that equation. H prime, I mean tetrabond Hamiltonian L n C n plus C L L L minus n power 1. Okay, equal to 0. This is equation number 4. Equation number 4. Now, if you clearly observe these two equations, you got two solutions, right? Non-trivalent solution of these two equations exist only if their determination of coefficients vanish. So I'm going to write that word also here. So in non-trivalent solution of these equations exist only if the determinant of the coefficients vanish. Okay, so if you write these two equations in terms of determination, okay, first one is h n minus e1 n h1 nl. This is h prime ln This is h prime ll minus en power 1. So determination equal to 0. This is equation number 5. So this equation is called Taylor equation. So this is called Taylor equation. Okay. So by using this equation number 5, this is very, very important steps. By using equation number 5, the corrected energies are one is, if you try to clearly observe here, one is En equal to En power 0 plus En plus 1. And second equation is En equal to En power 0 plus En minus 1. So here both the energies will be real as the diagonal matrix elements H prime LL equal to I mean both are, if both Hamiltonians, here two Hamiltonians are there. If you clearly observe here, two Hamiltonians are there. One is perturbed Hamiltonians H prime NN, another one is H prime LL. Okay, in case if the diagonal matrices are equal to the real as a diagonal matrix elements, the H prime NN and the H prime LL of the Hamiltonian operators are real, not imaginary. Okay, real here. So therefore, we can equal these two terms. So it is better to write by speaking. Very difficult. I can write sentences. Both the energies will be real as the diagonal matrix elements H prime NN and H prime LL of the Hermitian operators, both Hamiltonians. Okay, unperturbed Hamiltonian is the real. This is the condition. So by using this one, we can write like this: H prime NN equal to H prime LL, and H prime NL equal to 0. Therefore, we can write this equation En plus equal to En minus. And important one is the degeneracy is not removed in first order by using this equation number 3 and equation number 4. So we can calculate Cn and mean constant values, real values. The values of Cn and Cl will give En equal to En power 0 plus En plus power 0 and En equal to En power 0 plus En power minus. Okay. So if you want to n-fold degeneracy, or for example, I want alpha fold degeneracy. If, for example, this energy level is degeneracy, say, is alpha fold degenerate, then we can write this equation, linear combination equation, Cn sin power 0 plus C2 psi 2 power 0 plus and so on, plus I need up to alpha psi alpha power 0. Like that, you can calculate 3-fold degeneracy, 4-fold degeneracy, 5-fold degeneracy. So here we are considered only 2-fold degeneracy, right? This is enough, 2-fold degeneracy. This portion is very, very important. So if you can't get by using this secular equation, these two equations, just please try to comment below. I will explain this. Okay, you'll get easily this one. You can understand. So these two equations are very, very important. Uh, so if you want to explain this alpha fold degeneracy in terms of secular equation, then I can write then secular equation equations are this is a secular equation alpha fold, right? Then I can write secular equation like this. And so on up to 1 alpha, this one. Okay, second one to 1. Here the h 2 minus en power 1 and so on h prime to alpha, so on, so on and so on. Final one is alpha 1 h prime alpha 2. So this means here the h prime means, if I use some a different letter here, this is a tetrabroad Hamiltonian. Okay, tetrabroad Hamiltonian alpha alpha oxygen power. This is the alpha fold degeneracy values secular equation. So this is all about this degeneracy rates. Next class we're going to discuss very important one, first order Stark effect in hydrogen atom. The Stark effect in hydrogen atom we already discussed. Non-degeneracy case. This is degeneracy case, more important than the non-degeneracy case. Okay.